Okay, so in the last video, I talked about when we talk about the chain rule, we want to always consider an actual image of a chain. So if I have my outside function, that's what I'm going to do first before I take the derivative of the inside function. And if I have a third function, I would then take the derivative of that inside. So we're actually forming a chain, and we have to remember that if the original question involves a product or a quotient or a power, we're also taking into consideration those derivative rules. So let's start off f prime of x. So we're going to treat the outside function like x squared, what we would do with x squared. So I'm going to take the power of 2 over here, and I'm going to bring that down. I'm going to take my original function, negative 4x squared. I'm going to take the power of 2 that was originally there, and I'm going to subtract 1 from it. And all of this is taking the derivative of the outside function. And now I have to remember that this is not x squared, there's an inside function as well, negative 4x squared. So I have to multiply all of this with the derivative of the inside function. So negative 4 times 2 is negative 8. And x to the power of 2 minus 1 is x to the power of 1. And this is the derivative of the inside function. Now, if I was given a specific value of x, I could just substitute the expression right here. But what I'm going to do instead is simplify as much as possible. First, I want to get rid of my powers that need to be subtracted. So 2 times negative 4x squared to the power of 1 times negative 8x to the power of 1. Well, negative 4x squared to the power of 1 doesn't change that function. So we can actually delete that part right there. And now we can simplify. So f prime of x is going to be equal to 64x cubed. Any questions about that? Yes, Angus.
So, like for questions that we do substitute, are we expected by first?
I don't understand. No, when you're given a specific x value, I did examples yesterday with a specific x value. So I reviewed the video example at the end, but no, you could potentially substitute x right into this line, the x value, right? But you have to show the substitution. Students sometimes just write the substitution, the x value, and don't put any step in between until you get the final answer. I have to follow the substitution as well and see that you're multiplying and adding incorrectly. So please be aware that when you're skipping too many steps, there's always the possibility of losing marks. Okay, so you want to be as detailed as possible, especially because you're coming from an experience where you did most of MCR, or not most, but a bit of MCR through COVID. So you might not have had enough practice with the detailed solutions that are required for a prerequisite course in grade 12. So please take extra care to show detailed solutions. And that's why we do so many examples in our lessons. What I do in my lessons is what you're expected to do on your test. If I don't skip steps, you shouldn't be skipping steps, okay? There's always room to lose marks when you skip too many steps. Now, here is a harder question because we have a power and we have a power that is an exponent. This is actually 16x squared to the power of 3 over 4. So again, the power rule comes into play, and we're going to apply the chain rule to this. So f prime of x, I'm going to take the outside first. I'm going to bring down the 3 over 4. multiplied by 16x squared. And I'm going to take the original 3 over 4, and I'm going to subtract 1. All of this is the derivative of the outside. Now, the derivative of the inside function is simply 16x squared. So 16 times 2 gives me 32. X to the power of 2 minus 1 gives me the derivative of the inside function. I want to simplify this component. So I'm going to take 3 over 4 16x squared. I want to convert to a common denominator. So 3 over 4 minus 4 over 4. And all of this multiplied by 32x. Full screen mode to see if that's going to help a little bit. Okay, so once we get to this step, I'm going to rewrite this as 3 over 4 16x squared to the power of negative 1 over 4. Now that negative 1 over 4 only applies to the 16x squared. And we're multiplying all of this by 32x. Now let's think. If this, what I put in the red box, that has to be flipped and converted to a quartic root, right? To the power of 4 means the index has to be 4. And this fraction that has a 4 in the denominator, I can also expect that to be in the denominator. So I'm going to write, okay, so let's see, 4 times 16x squared to the power of positive 1 over 4. I want to take it step by step. By flipping it to the denominator, the exponent has become a positive 1 over 4. I'm now going to take the 3 in the numerator and put it up here. I'm going to multiply that with the 32x. Now give me 1 second. I'm going to stop sharing. And I'm going to pause my... Okay, so how do we go further from here? I'm going to extend the page a little bit and take my blue. So 3 times 32x is going to give me 96x. And now I have to fix my denominator. So if I have 16 to the power of 1 over 4 times 4, that's going to give me the number 8. X to the power of 2 to the power of 1 over 4. If I just multiply those, I get x to the power of 1/2. Now remember, this 96 can be divided by 8, and x to the power of 1 divided by x to the power of 1/2, essentially what I can do is, I'm going to actually write this as another step, is 96 over 8, and I have x to the power of 1 minus 1/2. My final answer is going to be 12 root x. And someone asked a good question the other day. It's always a good idea to write, even if you haven't been writing f prime of x for each line, for your final answer, you should have f prime of x is equal to 12 root x. So you see how I didn't necessarily have to show this step. I showed this step more for you so you could follow what I'm doing. But you see that I'm not just solving this in 2 steps. So when you try to do that, we can't read what's going on in your head. And it's especially because when you're taking virtual tests, it's really important to include your steps. I cannot reinforce that enough. Okay, so we're going to do about 4 examples for this first video before I give you 4 more examples, before I give you some time to study. Okay, so y is equal to 4x plus 1 squared. Now, I could write y as dy over dx or y prime. I'm going to choose dy over dx, the derivative of y with respect to x. I'm going to take this power of 2. Now, we're starting with 4x plus 1 squared because we've been dealing with monomials, and now I wanted to show you an example with binomials. I have to take my 4x plus 1 to the power of 2. And I want to make sure to subtract 1 from that. And then I want to take the derivative of my inside, which is equal to 4. So dy over dx is equal to, well, 2 times 4. I can simplify that and have that equal to 8. 4x plus 1 to the power of 2 minus 1 is 4x plus 1. But I'm not going to leave the question like that. I want to fully expand the question. Dy over dx. And so I'm using distributive property here. 32x plus 8. Now, this is still the equation to help us find the slope of the tangent. It's not the equation of the tangent line. It's the equation that helps us find the slope of the tangent line. Even though that's a linear equation, please don't confuse the two. In every lesson that I've done, I have showed you the 3-step process to actually find the equation of the tangent line. This is just, the derivative is just the slope of the tangent line. The equation that helps you find the slope of the tangent line, that is why it's not always a linear equation. Sometimes a quadratic equation, a cubic equation, because by substituting specific values of x, that's how you get the slope of the tangent line. And you need clarification on that. I did cover it in the last chain rule video, as well as all of the videos I posted. Now, this is a binomial as well, but it has a negative exponent. Yes, Arjun? For chain rule? Like it depends on the question. Something simple like that. You're going to have to show me the actual example, okay? I can, where you can expand, where it's not super complicated, expand, okay? But you'll have to show me specific examples if you have questions. Okay, so now we have dy over dx is equal to, I'm going to bring the -3 down. So notice the outside function, I'm still following the same procedure. However, for the inside function, it's going to be more complex than when we were just dealing with monomials. So I have x cubed minus x to the power of -3. Now that power of -3, I have to subtract 1. Multiplied by the inside function. So the derivative of the inside function is 2x squared minus 1. That's the derivative of the, not 2x squared. It was, what am I doing? That was a 3. It's to the power of 3. So I'm actually multiplying by positive 3x squared minus 1. Okay, now right away when you're dealing with negative powers, I want to write, I think, the whole question, simplifying all powers first. So negative 3 x cubed minus x to the power of negative 4 times 3x squared minus 1. Now I'm going to put a box around this power of negative 4. Because it has a power of negative 4, I want to flip that to the denominator, and I want to place that in the denominator. So I'm going to have x cubed minus x to the power of positive 4. Always remember, when you're moving something to the denominator, you need to change it to the power of positive 4. And then we have a negative 3 times 3x squared minus 1. None of those have anything to do with a negative power, so we can keep those in the numerator. Okay, now we want to see, well, how can we? Sometimes we could, should we expand it? We can expand it. So I can see how Arjun was saying some examples might not have been expanded, but we're going to try to actually take the, where you don't expand, sometimes it's just taking out the greatest common factor. So for example, dy over dx, my numerator can stay the way it is. The greatest common factor has been taken out, but we can take still a greatest common factor out of the denominator to have x times x squared minus 1 to the power of 4. Now, because this is a more complex question where if you had to expand, you'd have very large numbers. Here we're doing the opposite. We're just making sure everything, the greatest common factors have been taken out, and we're leaving everything in factored form. I'm circling the GCFs in green. Okay, so that would be an example where you leave things in factored form as opposed to expanding. But when the question is very simple, where all you need is a simple distributive property to complete the question, in that case, you would expand. With calculus and especially your first year university courses, you're going to notice that you have to sometimes use your best judgment based on your math background, what you think would be the best type of solution to leave your final answer in. But you'll notice there's still multi-steps, many steps required. So for the last two examples for today, I'm going to be doing a lot more examples on Monday for chain rule. I'm going to focus on square roots because that tends to give students quite a big bit of trouble with derivatives, because you have to convert to rational powers, powers that are fractions. Rational powers, powers that are fractions. So before I go into my dy over dx, I want to rewrite this question without the radical. So I want to write it as y is equal to, and there I go again. I don't want a radical here. I want 2x minus 3x to the power of 5. And I want all of that to the power of 1/2. So now when I go to my dy over dx, I'm going to take the power of 1/2. I know I have a power of 1/2 that I'm going to have to subtract a value from. But I have 2x minus 3x to the power of 5 to the power of 1/2 minus 1. And all of that, that is just my outside. Now I have to take the derivative of the inside. I have to multiply everything by the derivative of the inside. So the derivative of the inside is a binomial. That would be 2 minus 15x to the power of 4. Please stop me if you can't see why that is the derivative. Now I want to rewrite this entire question without any powers that need to be subtracted. So I have 1/2, 2x minus 3x to the power of 5 to the power of negative 1/2, all multiplied by 2 minus 15x to the power of 4. Now, how am I going to move that down? Oh, there we go. Okay, so just like before, I'm going to single out my components that have a negative exponent. That's going to be flipped to the denominator, and the power is going to be changed to a positive exponent. This 2 that's in the denominator is also going to, the 2 that's in the fraction is also going to be part of the denominator in my answer. So let me do that right now. So dy over dx is going to be equal to, so there's a 2 from the fraction, then I have 2x minus 3x to the power of 5 to the power of positive 1/2. I could rewrite that as a square root if I wanted. And what I'm left with in the numerator has a 1 over here. That's not going to affect anything. So I can just write this component 2 minus 15x to the power of 4. I would go one step further and I would rewrite this question with the square root. Let's see. I could take a possible x if I wanted out, but I'm just going to leave it like this right now. Notice there is no greatest common factor in the numerator, and even if we took, we factored this, it can't be taken outside of the square root. It's still included inside of the square root. So I would kind of leave my answer like this. But you see how a very simple radical question turns out to be a complicated derivative. There are so many rules attached to it. Now think in your head of a complicated original question, how complex the derivative will be. Sometimes when you have, and I'm going to do some examples next week, when you have the power rule, you have to apply the chain rule twice in the same question. We're going to leave that for Monday. Very last question that we're going to do today, just to reinforce that the index in the radical is very important. This is a fifth root. Don't assume when you see the radical sign that it's automatically a square root. Pay attention to the index to know what kind of root that you're dealing with. So I'm going to rewrite this question as 2x plus 3x squared minus x cubed to the power of 1 over 5. So dy over dx Gonna bring that 1/5 down. I'm going to write my 2 plus 3x squared minus x cubed to the power of 1/5. I have to remember to subtract 1 from that. So subtract 1 from that. But I can't stop there. And often students stop there. And they forget that this is the chain rule. So we have to take the derivative of the inside. So all of that, I'm going to multiply by the derivative of the inside, which is 6x squared minus, 6x minus 3x squared. That happened. Okay. Write the entire function, so we don't have any powers that we need to subtract. 1/5, 2x plus 3x squared minus x cubed to the power of negative 4/5. So this lesson has been having, we have a lot of examples where we have negative powers and negative powers that are also fractions. So again, I want to highlight what is going to be in my denominator for my answer. So definitely the 5 in the fraction, as well as this component all in here. And I'm going to leave it in fractional form and instead of trying to convert it to a radical root form. So my denominator, let's work with the denominator first. I have the 5 there. I have 2 plus 3x squared minus x cubed to the power of positive 4/5. Notice I don't have to go any further because there's no greatest common factor. There's no greatest common factor I have to take out of the brackets. And then in my numerator, all that I am left with is 1 that affects and nothing, doesn't affect anything, and the inside derivative from the chain rule. But in this case, the inside derivative can be broken up into the greatest common factor. Greatest common factor is 3x. So I basically want to factor 6x minus 3x squared. I always want to do that because there's a possibility for any constant numbers here or greatest common factors here to be in the denominator to be canceled with what is happening in the numerator, the greatest common factor. In this case, 5 and 3x cannot be canceled. So I would leave my solution like that. Angus.
So what's the reason that I don't think
Okay, 1 second. Let me just stop here for part 1.